feel the vibe.
What's up, guys? Welcome back to another Algebra 2 instruction video here with Mr. Gaines as we continue to explore linear systems in 3 variables. So the last video we took a look at algebraic methods to solving linear systems with 3 variables, and we're going to continue that process here. So let's jump right into some examples. Here I have an example that is C in your notes packet, and we have 3 equations, each containing 3 variables. And so we want to solve this linear system. And the method that we worked on was elimination. Using elimination to create a 2-variable, 2-equation system from this 3-variable, 3-equation system. So what I'm going to go ahead and do is I'm going to go ahead and, again, label just the equations. You don't necessarily have to do this, but it makes it easier for me to kind of explain what I'm working with here. So as I take a look at A, B, and C, these equations, I may notice that I can easily eliminate the variable y. If I just take B and add that to C, that's going to get rid of y. So B is 3x minus 2y plus 4z equal to 2. C is 4x plus 2y minus 6z equal to negative 7. If I add these two together, 4x plus 3x is 7x. The y's would subtract out to 0. 4z minus 6z is negative 2z. And 2 minus 7 is negative 5. So I have combined B and C to eliminate y. I want another 2-variable equation with the variables z and x. So again, I want to eliminate y. So if I take a look again at my equations, I can't use B and C again. I want a different pairing. I may notice that I can easily, or pretty easily, eliminate the combination of A and B. So if I double A and add that to B, that's going to eliminate the y values as well. So doubling A, multiplying A by 2 would leave me with 4x plus 2y minus 6z equal to negative 6. And adding b, I would have 3x minus 2y plus 4z equal to 2. Now we want to add these two equations together. So that's going to leave me 7x minus 2z equal to negative 4. And so now I have a new system. So I'm going to take those two equations and create the new system. So this is 7x minus 2z equal to negative 5 in combination with 7x minus 2z equal to negative 4. Now you may look at those equations and notice something there that seems a little off. The two equations are exactly the same and they equal different numbers. Let's take a look at what happens if I'm going to try to solve for these. So I'm going to use the elimination method again. I'm going to multiply that second equation by negative 1. So I'm going to leave the first equation the same, multiply the second equation by negative 1 to eliminate some variables here. And when I do that, the x's are going to subtract out, those z's are going to subtract out, so I'm going to be left with 0 on the left side of the equation and negative 1 on the right side of the equation. And so we get this statement here that's actually false. 0 does not equal negative 1. So it doesn't actually solve for any variables. And it gives us a false statement. All we see here is that I'm going to have what we call an inconsistent system. This system is inconsistent. We saw this in the last target where we had two lines that were parallel to one another. That's essentially what 7x minus 2z equal to negative 5 and 7x minus 2z equal to negative 4 would be, two parallel lines. And so in this case, there is not going to be a solution. So not all systems of equations are going to have solutions. So here we have an example of an inconsistent solution, or an inconsistent system that has no solution. Let's take a look at D. And let's work through the process of solving D. Now, what we may notice here in example D from the notes is that one of my equations already has just two variables. That is C. C has only the variables x and y. So then I already have one equation with two variables. I need to combine A and B in a way that's going to give me another equation with only two variables. The variables I want are x and y. So I need to eliminate z with A and B, and that can be done pretty easily. All I have to do is add A to B. So A is 3x minus 2y plus z equal to -1. And B is 2x plus y minus z equal to 5. So the z's already have opposite coefficients. So if I add these together, that's going to give me 5x minus y equal to 4. So now I have an equation here. Let's label this one D. And an equation C that are both linear with two variables. So I'm going to put them together. 10x minus 2y equals 8, and 5x minus y equals 4. Now you may notice something about this system. So this was equation C, and this was equation D. You might notice something about this system, but let's again take a look at what happens if I try to algebraically work through this. So I'm going to take C and add to that -2 times D, or subtract 2D. So C is 10x minus 2y equal to 8. I'm going to multiply D by -2, so that would be -10x. That would be positive 2y, and that would be -8. Now as I add these together, 10x subtracts out. The two y's subtract out, becomes 0. And 8 minus 8 is 0. So here I get a system where I don't get a true solution for x, y, or z, but I get a statement that is true. This would be a dependent system. And in this case, the solution would be all real numbers. Now, the numbers would depend on each other. That's why we call it dependent. So depending on what x is, y would have to be some version of x, and z would have to be some version of x and y. But we're eventually going to have all real numbers be part of the solution. So this is a dependent solution system, or a dependent system of equations, and would eventually have all numbers as being part of the solution. So we can see sometimes we come out with just a set of values, like we saw with examples A and B from the previous video, where we have an independent system, and it's always going to have a singular solution. Sometimes we come up with an inconsistent an inconsistent system of equation that has no solutions, or a dependent system of equations that has all numbers being solutions. Now I can describe my solutions a little bit further here in D. I could describe the relationship between x and y and z, and x and z, but that's not something that we're going to worry about here in Algebra 2. As long as we can figure out that this is a dependent system, then we have the appropriate knowledge for this question. So these are examples of linear systems of equations and how to solve them algebraically. The goal here is to get to applications, to be able to find a way to use these systems of equations. So let's go ahead and take a look at an example problem. So in problem 3 in your notes, it says a small business borrowed $225,000 from 3 different lenders to expand their product line. The interest rates were 5%, 6%, and 7%. Find the amount borrowed at each rate if the annual interest came to $13,000 and twice as much was borrowed at the 5% rate than was borrowed at the 7% rate. So we have a lot going on here. One of the things that we can do is we can start to identify important information and put that together in variables. We know that we are borrowing from 3 different lenders with 3 different rates. We want to find the amount borrowed at each rate. So let's let X be the dollar amount at 5% interest. Let's let Y be the dollar amount at 6% interest, and let's let Z be the dollar amount at 7% interest. So it's always good to start by identifying what your variables mean. So x is the amount at 5% interest, y is the amount at 6%, and z is the amount at 7%. Now, let me take this information and try to put it together into some equations. So we know that in total we borrowed, or the business, I guess, borrowed $225,000. So the first equation is whatever the amount from x is, added to the amount of y, added to the amount of z is going to total 225,000. So that's our first equation. Now, we also know that the amount borrowed at each rate came to an annual interest of $13,000 in total. So we don't know how much was borrowed at each rate, but we know that whatever was borrowed at x, if you can multiply that by 5% or 0.05, that gives you the interest. Whatever was amount borrowed at 6%, if you multiply that total by 6% or 0.06 times y, that gives you interest. Same thing for z. So z would be plus 0.07 times z. In total, this is going to equal $13,000. The last thing that we know was twice as much was borrowed at 5% than at 7%. So 2 times 7 is equal to the 5% rate, or 2z equals x. So we have to double z to get to x because twice as much is borrowed at 5%. So z is half of x, or double z is equal to x. So this is our system. Now I'm going to go ahead and label these, as always, with an A equation, a B equation, and a C equation. Now what I can see here is that I have a system of equations with 3 variables other than C. C only has 2 variables, which is good. So what I need to do then is I need to find a way to notice that y is not a part of equation C. Y is not a part of equation C. So I need to find a way to eliminate y. And you can do this a number of different ways. But again, the goal is to make sure the coefficients of y would be opposites. So I'm going to take A, and go over here to the right, and I'm going to take A times negative 0.06. And I'm going to add that to B. Now this is going to give me a little bit of decimals, but that's okay. So negative 0.06 times x would just be negative 0.06x. Plus, I would have plus, let's just go ahead and write this as a minus 0.06y minus 0.06z. And then I'm going to take my 225,000 and multiply that by a negative 0.06. So let me go ahead and do that on the calculator just to make sure I get this correct. This would be negative 13,500. So again, I'm adding that to B. So let me go ahead and write down B, or equation B, which is 0.05x plus 0.06y plus 0.07z equals 13,000. So we add. When we add, I get a negative 0.01x. The y's would subtract out. I would get positive 0.01. Sorry, this right here should be a z, 0.07z right there. So positive 0.01z equal to negative 500. Now I could work with that equation as it is, but I'm going to go ahead and multiply everything by 100 just to get rid of my decimals. So this is negative x plus z equals negative 500 times 100 would be negative 50,000. Okay, so you didn't have to necessarily do that to get rid of the decimals, but I just multiplied everything by 100, as we have 100 as coefficients for x and z. Now, I've created another equation with only 2 variables. If I go back to C, I can see that I already know a value for x. I know that x can be replaced with 2z. So I'm going to go ahead and just take this equation C and substitute it in for x. So that is a negative x, meaning I'm going to have the opposite of 2z, or negative 2z, plus z equal to negative 50,000. So I just did a little substitution there. Just substituted again, just substituted in right there. Now I can solve for z. So that's negative z equals to negative 50,000, and then I could divide by 1, or negative 1. So z is equal to 50,000. That gives me a solution. Now I can use this to come up with other solutions. So I'm going to then take this 50,000 and substitute it in over here to solve for x. So if I do that, I would get 2 times 50,000 equal to x. So x is 100,000. Finally, I can take what I know for x, and I can take what I know for z, and I can substitute it into the equation for a that we have listed. So a would now be 100,000 plus y plus z, which is 50,000, equal to 225,000. So I would add the 150, or the 100,000 and the 50,000 together and subtract that from 225,000 to get 75,000. So my final result here would be x is 100,000, y is 75,000, and z is 50,000. So I do briefly want to put some context back to my answer. So let's say that the business borrowed $100,000 at 5%, $75,000 at 6%, and $50,000 at 7% interest. So there we have taken a scenario where we had 3 values that we were looking for. We created a system of 3 equations with 3 variables, and then algebraically solved that system to come up with a final answer. Let's take a look at one more application problem here before we call it a day. So problem number 4. Problem number 4 says, at a local fair, a bank invites attendees to guess the amount of $5, $10, and $20 gold pieces in a sack. Participants are told that there are exactly 250 coins with a total value of $1,875. If there are also 7 times as many $5 pieces as $20 pieces, how many of each gold piece are there? Well, let's start with our variables. We don't know the amount of $5, $10, or $20 pieces. So let's let x be the number of $5 coins. Let's let y be the number of $10 coins or pieces. And let's let z be the number of $20 pieces. We know that there's a total of 250 coins. So we don't know the values of x, y, and z, but together that amount must be 250. We know that there is a total value of $1,875. So the value of $5 pieces would be $5 times the number of $5 pieces, so 5x. The value of $10 pieces would be $10 times the number of $10 pieces, or y. And the value of $20 pieces would be $20 times the number of $20 pieces, or z. This is going to total $1,875. and $75. Finally, we know there are 7 times as many $5 pieces as $20 pieces. So our $5 pieces would be X, and this number is going to be equal to 7 times Z. So there are more $5 pieces. So we have to multiply the $20 pieces by 7 to get to the $5 pieces. So here we have a system of equations. If you feel comfortable at this point solving this system of equations, go ahead and pause the video, see if you can find a solution, and then check back to see if our solutions match up. I'm going to go ahead and go through the algebraic process of finding the solution. So I can see here that equation C only has 2 variables, x and z. Y has been eliminated. So I want to take A and B and eliminate y from those. So I'm going to take A and multiply it by -10 and then add that to B. So that would give my y's opposite coefficients, which is what we want to eliminate the y variable. So here I am multiplying each piece of that equation by -10. The equation for B stayed the same. So I didn't need to make any changes there to eliminate the y value. So I'm going to go ahead and add these 2 equations together. So this would give me a -5x. The y's would subtract out, plus 10z equal to, let's say -625, but let me double check that. So the -2500 plus 1875 would be -625. So now, I know the value for x as an expression is 7z. So I'm going to take this 7z and substitute it back into that equation for x. So -5 times 7z plus 10z equals -625. So -5 times 7 would be -35z plus 10 would be -25z. So -25z equals -625. Divide by -25, and I should get 5. Let me double check that just to make sure that's accurate. So 625 divided by 5 is, or sorry, divided by 25 is 25. There we go. Good thing I didn't roll with that. Oh, silly mistakes. So it's always worth checking your answers there. So I've got an answer for z. Z is 25. Now I can use the answer for z to find an answer for x. So I'm going to take this z and substitute it back into that equation. So x is 7 times 25, and 7 times 25 should be 175, which is accurate. So x would be 175. Now I can take my solution for z and my solution for x and put them back into the very first equation that I labeled as A to solve for y now. So x is 175, y is unknown, z is 25. That would equal 250. 25 plus 175 is 200. I'd subtract that from both sides to get y equals 50. And now I have solutions for each of my variables. So if you wanted to, you could check those solutions, substitute x, y, and z into each of those equations to make sure it is a solution for all of the 3 equations that we created, and then add some context. So there are 175 $5 pieces, 50 $10 pieces, and 25 $20 pieces. And there we have an answer. So we do want to make sure that once we finish application problems, we put our answers back into the context of the problem as we present our solution. So here we see a couple of examples of how to create a linear system of equations with 3 variables from a word problem or an application problem, and then how to solve that problem to come up with a solution. And this is a good place to finish for the SE2 Notes Part 2. Thank you guys for tuning in. And as always, we'll see you soon.